Hi, I'm Dustin Rubin, and I'm going to be doing an analysis of novelty metrics. I'm going to look at some simple novelty metrics and then see what happens when you combine them to create more complex novelty metrics. So there's a few different problems that can happen with novelty search. Sometimes you can basically explore a space where the robot is not functional. So one example would be like my robot flipped itself on its back and then just shakes its legs where it's not really moving. This is not really functional behavior, but it might be different on the novelty space that it's exploring. Another thing that can happen is it can be extremely slow to get useful behaviors. So if your metric isn't set up in a way to incentivize behaviors that are interesting or useful, then you might just get stuck exploring that space for a long time. So here's an example of a robot where, while it wasn't in a non-functional state behavior, it was sort of trapped in this area where it could continue to have new novel robots, but wasn't really creating new behavior along that axis. So basically my idea was, what if I could combine simple novelty metrics in order to create more complex ones that would incentivize the robot to constantly be exploring the behavioral space better or getting to higher fitness behaviors faster. Okay, so now I'm going to talk about the experiment I did. So basically I started with homework 6 where we had the evolutionary algorithm. And basically what I did is I changed out the fitness function for a novelty search. So basically this novelty search was written so that you could say which metrics you want or any combination of the metrics. So you could say I want this metric and this metric, but not the rest. Um, and then I also wrote the code so that you could store the average distance for a given population, but it was not being used as the fitness. I also used a tournament size of 2 and then population size of 50 with 25 generations. And then I ran each metric individually and then some combinations of those metrics. And I did 3 trials of each of those runs. So now I'm just going to quickly explain the charts that I'm going to be showing a bunch of. The 3 different lines are the 3 runs I was talking about. The fitness is the average distance the robot got away from the start of the environment. And as you can see, there's 25 generations of data for each of these charts. So for many of the novelty metrics, you can see that the robots didn't necessarily have to adapt how far they moved away from the start. This novelty metric was the average distance between the legs. So as you can see, it doesn't really incentivize the robots to move away from the start very much. So here's another metric that didn't really cause too much of a change in how far the robot moved away from the start. As you can see, it was coordination of legs. Basically how this was implemented was the difference of the angle between similar joints on the robot. And yeah, you can see that it's not quickly incentivizing the robot to move further away from the start. So here's an interesting result where I basically took the last 2 metrics and combined them together. So now we do the leg distance and the coordination of legs, and you can see that the results look a lot better. So here's an interesting example of that graph I just showed, where this robot has the coordination between legs and the distance between legs metrics. And as you can see, it kind of has sort of a spinning behavior where it's kind of running in a circle. So here's an example of all the single metrics. As you can see, the only one that gets a actual pretty significant increase on the fitness is the average speed, while the rest of the metrics don't really cause the robot to ever gain a significant amount of fitness. And here's another combination of 2 of the metrics that was able to produce an interesting result. Here's an example of a robot I got from that previous slides to novelty metrics, average speed and coordination of legs. A few things to take away from this was that combinations of metrics were very different from the scores that the parts of their metrics got. So it wasn't really like combining the best features of metrics, but more like creating an entirely new metric. One more takeaway I got from this project was that once I combined 3 or more of the metrics together, the robots became non-functional quickly. It seems that when you had that many different axes for the robots to try and be different on, it starts to cause some very strange behavior and a very lot of non-functional behavior. I think both of these conclusions are supported by my data in that the combinations of metrics did not have similar results to the individual metrics. Also, I didn't have any successful runs with 3 or more metrics combined. So that supports the idea that having that many metrics makes it harder for the robot to gain fitness early on.